Unexpectedly, JavaScript has become perhaps the most important programming language in the world, which is surprising because it's also the world's most misunderstood programming language. We'll try to fix some of that this week. So this is the outline for the course. Today is going to be a series of 5 lectures, and I apologize for that. There's a lot of information I need to give you, and the only way I know to do that is to say it. So you're going to have to listen to me whining on all day. But tomorrow will be much better. Tomorrow we're going to workshop, we're going to have fun with functions, you're going to be writing programs, and it's going to be great. We're going to have a much better time tomorrow. Then on the third day we'll do some more fun with functions. Then we'll also look at some very important topics: security, asynchronicity, which is something you have to deal a lot with, especially in servers, and the better parts, looking at the future of this language and other languages. So that sound agreeable? So let's begin with part 1, programming style and your brain. These are 2 topics which appear to have nothing to do with each other. Programming style is the part of your program that the compiler ignores. And some people think that because the compiler doesn't care, you shouldn't care. Any style is as good as another. It's just a matter of taste. I'm going to try to persuade you that that is not the case, that some styles are significantly better than others. And then your brain. Your brain is that big wad of meat in your skull that you think with. And what possible connection could there be between these 2 things? Well, it turns out there is a connection, a surprising and important one. I'm going to be misrepresenting the work of Daniel Kahneman, the Nobel-winning psychologist. Now, Nobel does not give a prize for psychology, so they gave him the award for economics. But he's not an economist. But he found that one of the fundamental assumptions of economics doesn't hold. That is, that in any transaction, a party can be expected to pursue their own best interest. Kahneman shows this is not the case if a party is a human being, because human beings do not think the way economists think we think. In fact, none of us think the way we think we think. And the more you study Kahneman, the more amazing it is that we ever get anything done at all. So Kahneman has a metaphor for human thought based on the interaction of 2 systems, System 2 and System 1. System 2, which we can think of as the head, is the higher level one. It's analytic, it's algorithmic, it's where we do mathematics and reasoning and logic. It's a really sophisticated machine. It requires a tremendous amount of effort to use, and it is very slow. So we leave it turned off as much as possible. It's because that system is so slow that we had to invent computers, because System 2 is not capable of generating all of the numbers that society needed in order to do its social evolution. So we needed to come up with machines to do that processing for us. Then there's System 1. System 1 you can think of as your gut. It is intuitive, it's heuristic, it's associative. It is very, very fast. It requires no effort, and in fact, you cannot turn it off. It's on all the time. And the idea that we have these 2 systems is not new. I mean, we all have this intuitive sense that we've got these 2 systems. And sometimes you can even hear them. Sometimes if you're confused about something important, you can hear your head telling you one thing and your gut telling you something else. I mean, we've all experienced that. What Kahneman found was how the 2 systems are connected. It turns out System 2 gets its assumptions, its givens, its working set from System 1, and is not aware of that connection. System 2 thinks it's getting this stuff from the vault of deep truth, but it's not. It's getting it from System 1. And System 1, because it's an approximate system, sometimes gets things wrong. And if you have a logical system with false inputs, you can get false outputs. And it turns out we do this all the time. Let me give you an analogy from visual processing. Visual processing is the opposite of computer graphics. It's where you take a signal from a camera and analyze all the pixels and try to determine what are all the objects in the scene and how are they all moving relative to each other in the camera. You need to be able to solve this problem in order to walk in the world. And it's a really, really difficult problem. But we're all able to solve it, and in fact all the animals are able to solve it. And the reason we're able to do that is because we don't solve the general problem, because the general problem is hard. Instead, we solve special problems, problems which are much easier to solve, but which sometimes give the wrong answer. And we have techniques for revealing the ways in which we get this wrong, and we call them optical illusions. So this is an illusion designed by Edward Adelson of MIT. And here we've got a checkerboard with white squares and black squares. And two of the squares are labeled A and B. And it turns out those two squares are exactly the same color. Some of you may be seeing that, you may believe that I'm telling you that, but you're looking at that and one is clearly white and one's clearly black. But in fact, they are both that color. They're both that shade of neutral gray. And in fact, if I overlay my square on top of the picture, if A and B were different colors, then you should see some break in continuity, right? You should see some edge forming, and you don't. Now, many of you may be seeing a gradient. Who is seeing a gradient here? Seeing the colors going from black and white? Come on. Yeah. Your brain is lying to you. There's not a gradient. It is that color. It is a solid colored square. You know the truth of this image, and yet you still can't see it correctly. It's because there's another part of your brain that Kahneman doesn't talk about, which deals with inconsistency, which is a really important thing to have, because if a computer system becomes inconsistent, there's a really good chance it's going to fail, right? It's just, boom. And biological systems can't afford to fail when they get confused. So instead, we've got this system which will reject information which is coming from the world through our senses if it contradicts our internal state. And that's why you cannot see this correctly, because it is altering what you're seeing with your eyes in order to conform with your patterns of image processing. And it turns out we do this all the time. It's not just in the visual system, it's in everything. And that's why we argue so much, because we literally cannot hear what the other person is saying. If the other person is saying something which contradicts us, then we will misinterpret what they're saying. It's not intentional, it's just part of what we're doing in order to resist inconsistency. And this is the mechanism. So it turns out none of this was news to the advertising industry. They had figured out a long time ago that they could design messages which would bypass the head, that would go straight to the gut, convincing us that we have to buy things that we don't need. They've been doing this for a long, long time. What Kahneman does is provide the theory which explains why that works. And I don't think anybody understood this better than the tobacco industry. Because you look at tobacco, okay, so how do you sell tobacco? What does tobacco do? It makes you smell bad, it turns your teeth yellow, it makes you sick, and then it kills you. So how do you convince people, let's buy some tobacco? And they do it by creating messages which are able to confuse System 1. System 1 is easily confused about the difference between slow death and good for you. So that is the equipment that we have for writing computer programming, or for writing computer programs. And programs are the most complicated things that humans make. There's nothing else in human experience which is composed of as many tiny little pieces which all have to go together perfectly, that have to work in real time with changing states and changing inputs in a dynamic situation. Nothing else comes anywhere close to the complexity that we have in software. And it's amazing that we're able to manage this, but it's really hard. So when the first von Neumann machine started coming online, and it was discovered programming is really, really difficult. There was a lot of thinking that we need to figure out a way in order to make it easier, in fact, to make it unnecessary, because otherwise the computers are not much use to us. And so that started research in artificial intelligence. And the goal of artificial intelligence originally was to figure out a way to have the computers write their own programs, because it was just too hard to have humans writing them. AI has had a lot of amazing successes, but they have failed completely at their original mission. That you cannot give a problem to a computer and ask it to write the program that solves that problem. If it were, then we would ask the computer, well, write a program that's better than you, and keep doing that until they become our overlords. And that hasn't happened. Computers don't know how to write programs, so we write them. So as a result of the failure of AI, we are still writing programs by hand. So the most important tool we have for doing programming is the programming language. Because one thing that computers are really good at is translating one formal language into another formal language. And that's what programming languages do. They allow us to write at increasing higher levels of abstraction, where we get more leverage, where we can create more work with less effort, and then the computer, or through the programming language, figures out how to convert it into a form that the computer can execute. And so programming languages are really, really important. The thing that makes programming so extremely difficult is the requirement for perfection. Programs have to be absolutely perfect in every aspect, in every detail, for all possible inputs, for all possible states, for all time. And the contract we have with the computer is that if a program is not perfect in all of those ways, the computer has license to do the worst possible thing at the worst possible time, and it is not the computer's fault. Whose fault is it? It's your fault. Why did you give us a program which you knew wasn't perfect? So you'd think, well, okay, because of that requirement for perfection, we would never release a program to production until we know it's perfect. And we don't do that for two really good reasons. The first one is we would never release a program to production. And eventually management would figure, or why are we paying these guys if they never finish? Let's figure out something else. But the second reason is much more insidious. And that is we have no test for perfection. It may be that someone once created a complex program that actually was perfect. There's no way to know. There is no test for perfection. We have tests for imperfection, but no test for perfection. So there's just no way to tell. Now, it's most likely that none of our programs are perfect. And so what we do is we put our programs into production hoping that we'll discover what's wrong with it and fix it before anyone else finds out, which is crazy, but that is the state of the art. That is the best we have figured out how to do. So we're doing this work with the brains of hunters and gatherers. And this is not a metaphor. Our brains have not evolved since the last ice age. And there was nothing in that experience to have prepared us for computer programming. You know, hunting and gathering required a completely different set of skills. So it's kind of amazing that we're able to do this at all. It's sort of lucky, but there's nothing in our evolution which has prepared us for this. So we're making use of everything we have in order to do this. So programming obviously is making use of the head of System 2, because that's where the algorithms live, that's where we do the analytical stuff, that's where we do the logic and the state and the dynamic stuff, all of that stuff. But we don't understand how we do it. You have all figured it out, but not well enough that you can write down a list of instructions. This is how you write a computer program. You do these things and hand it to someone else, and they can read it and follow those steps, and then they can write programs. We can't do that. Somehow we have all figured it out, but not well enough that we could tell someone else how to do it. And that's why we can't tell the machines how to do it, because if we could tell another human how to do it, then we could tell a machine how to do it, and we don't know. And much of what we're doing involves intuition, because we're always making trade-offs. It's never clear what the best approach to solving a problem is going to be. And usually we're trying to solve a problem with incomplete knowledge of what the solution is going to be, and so we have to guess. And System 2 is not good at guessing. System 1 loves to guess. System 1 will guess without knowing it's guessing. It's great at that. And so we look at a problem and we'll look at it top down and bottom up and take a macro view and a micro view. We keep constantly shifting our point of view until eventually a program emerges. And we don't know how we do that. System 2 is obviously involved, but I think System 1 is involved there as well. That's part of the reason why we can't document it. Now, I have no evidence to support that argument, but my gut tells me it's true, so I believe it. That brings us to JavaScript, the world's most misunderstood programming language. JavaScript has some of the best parts ever put into any programming language. It's extraordinary how good the good parts of this language are, and we're going to spend a lot of time exploring that. JavaScript also famously has more bad parts than any other programming language. And in the next hour, we'll talk about why that happened. But it does. Now, it turns out every programming language has good parts and bad parts. But very few languages have as much goodness as JavaScript or as much badness as JavaScript. JavaScript has everything from the sublime to the completely ridiculous. And the analysis I'm about to do, you could do on, and should do, on every language, but it's especially telling with JavaScript. So because JavaScript has so many bad parts in it, I wrote a program called JSLint. It's written in JavaScript, it reads JavaScript programs, and it warns you you're messing with the bad parts. And by cleaning that up and sticking to the good parts, you end up with programs which are substantially better, which are going to be more maintainable, closer to perfect. That's all good stuff. And it's free, and everybody should be using it. All of your code should pass JSLint without exceptions. You really want your code to be that good. But a lot of people don't want to do that because it comes with this warning, JSLint will hurt your feelings. And it's true. And I hear from people constantly crying, whining, JSLint, can you fix it so it doesn't complain about me because I'm awesome. And after a few years, I started wondering, oh, wait a minute. There's no crying in programming. We imagine ourselves to be the most rational computers in the world, or the most rational people in the world, right? Because we're the ambassadors to the computer. You can't bullshit computers. We imagine ourselves to be totally, completely logical about everything, superior to all ordinary mortals. But it turns out we get really emotional about things, about how we write our programs. Questions like tabs or spaces. Turns out there's not a lot of data to support one versus the other, but we get really emotional about it. Or do curly braces go on the left or on the right? You can toss that question into a room of programmers and all work is going to stop. And they're going to have these really emotional arguments because it turns out there is no data at all to support either argument. There's no data which shows you get better productivity or lower error rates, any important difference, but that doesn't matter. The arguments will be there and they'll be intense and they won't stop. And for this, I blame Ken Thompson. Ken Thompson is one of the most important programmers to have ever lived. We'll talk more about him later. He designed a language called B, which inspired the language called C, which inspired virtually all languages to happen since then. Really, really important contributions. And in those languages, you could put the curly brace on the left or on the right. Thompson put them on the right, just seemed right to him. And his partner, Richie, also put them on the right. But there are other people in their lab who wanted to put them on the left. And I'm sure they had a meeting. And it probably went on for days. And at some point, Thompson said, leave me alone. I don't care. I don't care. Leave me alone. Which is a shame, because he could have said, I'm fixing my compiler so that you have to put them on the right. And if you put them on the left, it's going to be a syntax error. If he had done that, who knows how many man-centuries of time we could have saved. But he didn't. So we were still arguing about it. And it's an emotional argument. So there are some things that we can't agree on. Everyone will agree that you should be consistent. You should always put them on the left or you should always put them on the right. You shouldn't mix it up because it looks stupid. And we're trying really hard not to intentionally look stupid, so you don't want to do that. And everyone will agree that however they do it, everyone else should do it that way too. That's easy. But we can't agree on what that way is. So if you have someone who is used to putting them on the left and he goes to work for a shop that puts them on the right, and they're going to say, well, that's how we do it. You got to put them on the right. He's going to start to cry. You go, no! And he's going to start trying to come up with reasons for why this is wrong. And the gut is saying, this is wrong, this is wrong. And system 2 is going, yeah, I know, that's wrong. Why is that? And it starts rationalizing. It's trying to come up with reasons to support its deeply held belief. But there are no reasons. And so you hear yourself saying things which are completely ridiculous, and that just makes you madder. And the madder you get, the more, and it's just this, and it ultimately doesn't make any sense. It's sort of like driving. In some countries they drive on the left, and in some countries they drive on the right. And there's no data to support one versus the other. You don't get better fuel efficiency or lower accident rates on one side or the other. But wherever you are, it's a really good idea that everybody be driving on the same side. And this is kind of like that. We know that there should be one answer, But coming up with the one answer is really hard, and leaving it to chance or leaving it to personal taste is not a good predictor of any kind of outcome, and so we could keep wasting time on this. So ultimately, I don't know what the correct solution to this is, except in JavaScript. And in JavaScript, I'm absolutely convinced you should always put them on the right and never on the left, and here's why. So one of the really nice things about JavaScript is we can have a function that returns an object. Sometimes you call those constructors. And JavaScript provides this really nice thing called an object literal, where we can return a new object. That's very, very nice. And if you put the curly brace on the right, it does exactly what you would expect. But if you put the curly brace on the left, you get a silent error. These are the worst kinds of errors. You don't get an error at compile time. You don't get an error at runtime. What will happen is your function, instead of returning a new object, will return the undefined value. So it doesn't fail here. It's going to fail somewhere downstream from here, where something will go to operate on an object, and it's not there, and boom, the program blows up. And so you're going to have to debug this thing. And you may eventually trace it back to this line, and that looks right. Where did my object go? You can easily waste a lot of time on this. So let's look at what happens. Let's zoom in on this. So as we're going to find out in the next hour, JavaScript was designed as a language for beginners. That was the original goal, was to make a beginner's programming language. But it also looks like C. And C was not designed for beginners. C syntax is really fussy. It's way too complicated, especially if you're going to give it to people who haven't had much training. So how do you deal with that? But I think the correct answer would be design a new syntax which is simple and clear. He didn't do that. Instead, there was a feature called automatic semicolon insertion, which would attempt to insert semicolons in places where the beginners wouldn't know that they had to go. And unfortunately, it sometimes doesn't put them in places where you think it should, and it sometimes puts them in places where you think it shouldn't. And this is one of those times. So automatic semicolon insertion will put a semicolon after that return. Now we've got all this other stuff. You would hope that something is going to snag a syntax error so we can get some warning. For example, we've got the curly brace, which opens up the object literal. Except when you move that curly brace into statement position, it becomes a block. So there's this syntactic ambiguity. Now JavaScript doesn't have block scope, so there's no value in having naked top-level blocks, but it does, so that masks this error. Then we've got OK colon. OK colon doesn't look like a statement, but it does look like a label. Now, the C language had a goto statement in it, which meant that you could transfer control from one statement to any other statement. And we have since determined that goto is harmful, so we don't use it anymore. It does not exist in JavaScript. Hooray for JavaScript, it's better than C in that respect. But JavaScript syntax still allows every statement to have a label, even though there are only 4 statements that make sense having labels, because they make use of labeled break. And that is not one of them. So that's bad. Well, then we've got a false statement. Well, a false statement doesn't make any sense. But there's another thing we inherit from C, which is the useless expression statement. That we can take any expression, put it in statement position, put a semicolon on the end of it, and it's now a statement. Now, in my view, there are only 2 expressions that make sense in statement position, assignment and invocation. Everything else, I think, should be a syntax error, but it's not. So this is allowed, and the compiler will look at it, go false. Yep, you're still constant. Good. It'll just go on. Then, but if it's a statement, it needs a semicolon. Not a problem. We've got semicolon insertion, so it comes in and inserts that. Now there's a semicolon at the end of the block. Blocks do not end with semicolons. But there's another feature that we inherit from C, which is the empty statement. So anywhere you want, you can have extra semicolons, and they all get soaked up. Then all of this is unreachable code that you can't possibly execute something that comes after a disruption. But JavaScript's okay with that. It allows anything you want after a return statement without any warning. So if you write code that looks like that, the compiler thinks you're writing code that looks like that. You might be thinking, this is the stupidest thing I've ever seen. And you're probably not wrong. But that's how it exists. That's what this silly language does. So if you put your curly brace on the right, you will never experience this. And if you put your curly braces on the left, this is waiting for you. So in thinking about programming style, let's look at the trade-offs here. So what is the cost of putting a curly brace on one side versus the other? 0, right? There's no cost, it's just punctuation. There's no cost. What's the benefit? The benefit is you will never waste time on this bug. This bug will never exist in your program. Is that a good benefit? If you can get it for free, yeah, absolutely. So that's why in JavaScript I recommend always put your curly braces on the left or on the right, never on the left. You should prefer forms that are error resistant. You should be coding in a way which makes it harder to form new errors. The switch statement is another of Thompson's things. It was modeled after, or inspired by Tony Hoare's case statement, which was a brilliant idea that we will have several independent clauses and we will pick one of them based on the value of an expression. Brilliant idea. But Thompson reinterprets it in the form of a computed goto, which is another thing that was in Fortran, which we've since decided is a bad idea, except it survives in almost all modern languages in the form of the switch statement. And the hazard is the fall-through hazard, that in any case, if you do not explicitly disrupt, it will automatically fall into the next case. And early on when I was developing JSLint, someone wrote to me and recommended that JSLint give warnings on this, because it's really difficult to look at the code and observe that one case is falling through into another, because the syntax is designed to obscure that fact. And I thought about it deeply, and I wrote back to him and I said, I can understand that hazard, but there's this wonderful elegance that you can get if you can cause one case to fall into the next one. And that's a valuable thing. And the error can happen, but it hardly ever happens. And so, given you've got this good thing that can happen versus this unlikely bad thing, I'm not going to test for that. I'm not going to give warnings on it. I think this is actually a good part of the language. The next day, the same guy wrote to me and said, I found a bug in JSLint. So I said, okay, good, thank you. I opened the debugger, and it turns out, you know where this is going, right? I had a case that was falling through. And in that moment, I achieved enlightenment. Because it turns out we spend most of our time making and fixing our own bugs. We think, what I do today, I was power typing, I was typing, no. We spend most of our time saying, my God, what have I done? And then we find it, and we get this little rush of euphoria, oh, I did that again, boom, and we forget. And so we have all this lost time. We forget about how much time we spend chasing bugs. And we fail to learn from our mistakes. But on this particular occasion, it was so humiliating, because I had just given a speech about how this was a good part, and then I'm shown by the same guy a bug in my own code that was caused by that thing that I was defending. And because it was so humiliating, I could not avoid learning the lesson, which was, if I never intentionally fall through, I can find the cases where I accidentally fall through. And that turns out to be much more valuable. And it caused me to re-examine my analysis, and it turned out I was completely wrong in every aspect of it. I thought I was being so logical in measuring the trade-offs, but I wasn't. Where I said I was arguing in favor of that wonderful elegance, no, it turns out that's a really bad thing, because it causes coupling of these clauses which should be independent. And that means that the code is now really brittle, that if you need to make a change to one clause, that's going to affect other clauses which can now be spilling into it. So you're making the program harder to maintain. You're making it more likely to have bugs introduced to it as a result of its going through simple revisions. Because what we should always be doing is trying to uncouple things, right? But this causes an implicit coupling, which is bad. But even worse was when I said, That hardly ever happens. That's another way of saying it happens, right? And we don't want it to ever happen. It's not like we don't want it to happen very often. We want it never to happen because we want our programs to be perfect. We can't tolerate it ever going wrong. This is System 1 talking. System 1 is terrible at math. System 1 gives most more weight than all. System 1 thinks 0 and not very many are the same. They're not. Anytime we're making mathematical arguments without any data, that's probably System 1 talking, and there's a really good chance we're wrong because it's guessing. It doesn't know. And we do this all the time. So a good style can help produce better programs. Style should not be about personal preference or self-expression or taste. It should be about reducing your error rate. Every decision we make about how are we going to code this thing, how are we going to express this thing, it should be about how are we best going to make a program which is going to be perfect, because ultimately that's the goal. Now we can get some clues about programming style from literary style. The Romans wrote Latin all in uppercase with no word breaks or punctuation, and it worked for them. You can go to Rome and you can still see these letters. We call them Roman letters today because that's what they used, engraved in stone. It looks just like this, except they were writing in Latin, but it's the same letters. And it worked for them. They had a very powerful civilization that took over a large part of the world, held it for centuries. Although there are ambiguities in this. For example, I can read the third line as now or DB reeks. It's a possible reading. So those sorts of ambiguities can lead to errors. But it worked for them for a long time until Constantine establishes Christianity as the official religion of the Roman Empire. At this point, it becomes necessary to make copies of these documents and distribute them all over the world. And the problem is they don't have originals for any of those documents. All they have are copies of copies of copies of copies. And it turns out no two copies agree. That every time they are copied, they mutate. And that's a problem if you're trying to establish an institution that derives its authority from the word and nobody can know for certain what the word was. So medieval copyists introduced lowercase, word breaks, and punctuation into their manuscripts. And these innovations helped reduce their error rate and made it easier to copy a manuscript without introducing errors into it. And that was a really important innovation. It also, unexpectedly, made the manuscripts easier to read. So when Gutenberg begins printing with movable type, he copies those conventions. And we're still using them. We now have centuries of experience with literary style, using lowercase, word breaks, and punctuation in a particular way. We've all been trained since we were children to read and write in that style. And that turns out to be really valuable. That you can easily tell the difference between good writing and bad writing by does it conform to this or not. So good use of style can help reduce the occurrence of errors. One of my favorite style manuals in English is The Elements of Style. It's a little pamphlet that was self-published by William Strunk about 100 years ago. It's since been updated by E.B. White. And it needed to be updated because English has continued to evolve since then. But most of Strunk's advice is still really good. And a number of computer scientists have used it as a model for writing books on programming style very, very effectively. So programs must communicate clearly to people. We should think of our programs as literary works. And it's at least as important that they communicate what they do to people as they do to the machine. It's not good enough to write something that's really sloppy, thinking that, well, if I can get it past the compiler, I've done my work. Because if the program's ever going to be used more than once, it's going to be necessary for somebody to be able to understand it and make it better. And so we need to make the programs communicate what they do in order to allow us to do that. Otherwise, we're setting ourselves up or others for failure. So we should use elements of good composition wherever applicable. And I think we should, for example, use a space after a comma, not before a comma. That's how we do it in literary style. In a programming style, we should do the same thing unless we have clear evidence of a benefit that occurs from that difference. Because we already have all this education locked into our brains about those sorts of patterns. We can use that to make it easier for writing our programs. Now, programming requires significantly more precision than writing does, so we'll need additional rules. For example, I propose that we use spaces to disambiguate parens. We use parens to indicate parts of statements, to indicate invocations and function definitions, and grouping. And so to help us to distinguish those cases, I propose a rule: there is no space between a function name and a left paren, and there's always one space between all other names and a left paren. So by that rule, these forms are all wrong. For example, return is not a function in this language, so we shouldn't make it look like a function invocation. Now you could argue, well, someone could easily figure out what these mean, right? So it doesn't matter. But it does matter, because you want the person who's reading your program to understand what the program does. You don't want them to be mentally correcting you and proofreading you, because that is distracting them from the much more important work of figuring out what your program does and how do we make it better. So one of the good parts in JavaScript is the immediately invocable function expression. And we'll look a lot at these much more later today. And unfortunately, the design of JavaScript didn't anticipate that this was a feature of the language. So here we've got a function statement, and we want to invoke that function immediately, but we can't. It's a syntax error. Someone figured out that we can wrap the function in parens. That function is now in expression position, and now we can immediately invoke it. But then you've got the extra invoking parens hanging off on the end like a pair of dog balls. So we can do better for the reader by wrapping the entire invocation expression in parens. So now the goal is not to just get it past the compiler, but to give a little bit more information to the reader, so that when the reader sees a function and the closing parens wrapped in parentheses, that means something. That means what's important here is not the function, it's the result of the function. And just by moving the paren one space over, we give a little bit more information to the reader, and that can be helpful. And again, we do it at no cost. So you remember earlier I warned you about automatic semicolon insertion, how it sometimes puts them in places where you think it shouldn't, and sometimes doesn't put them in places where it should. This is one of those times. So here we've got an expression statement. Someone left out the semicolon, expecting that the system was going to add it. But in this case, the system is not going to add it. So instead of assigning y to x, we're going to assign the result of calling y as a function, passing the result of the other function as its argument, which is not how anybody would read this, but that's how the compiler reads it. And so I recommend never rely on automatic semicolon insertion. Always put the semicolons in the right place. If you're not sure where that is, JSLint will be really happy to tell you where they go. JavaScript has a with statement, which was modeled after the Pascal with statement, which was intended to make it easier to write certain kinds of function access or object accesses. Unfortunately, it wasn't designed correctly. So here we've got a with statement, and here we have 4 statements that it expands into. Can anyone guess which of these that will do? Anybody?
I think it's the first one.
Actually, it's a trick question. It could be any of them. There's no way you can tell by reading the program which of these it's going to do. And in fact, it's possible that every time that statement executes, it could be a different one.
Depends on O?
Yeah, it depends on O. And since you can't know what O is at compile time, there's no way to read the program. So we want to be confident that our programs are perfect, but how can you know that your program is perfect if you can't even read the program and know what it does? So for that reason, I recommend don't ever use the with statement. You don't need it, leave it out, you're better off without it. Now, there are a lot of very clever uses for the with statement, and the people who discover these clever uses think that they should be entitled to use it because it's so useful. But I'm not saying it isn't useful. I'm saying there's never a case where it isn't confusing. And confusion is the enemy. Confusion must be avoided. Confusion is when a program appears to do one thing and it actually does something else. Another word for that, bug. We don't want bugs. So I want to eliminate as many sources of confusion as possible because I'm trying to attain perfection. I may never get there, but God Almighty, that's where I'm going. I want to try and make programs that are perfect. JavaScript has a double equal operator. I have problems with that. I think it should have been called equal, but that's another thing that Thompson did to us. But unfortunately, even worse than what Thompson did, it does type coercion. So first it looks at the two types of its arguments, and if they're not the same type, it will convert one or both of them to another type and then compare that result. And as a result, you get false positives, and it also means you lose transitivity. Transitivity means that if two things are equal to the same thing, then they should be equal to each other. That's not the case here. So when JavaScript was developed, this was thought to be a good idea. It turns out it's not. So the inventor of the language realized he'd made a mistake. So when it went to be standardized, he went to the standardization committee and said, I screwed up the double equal, but I know the fix for it. We just have it not do type coercion. I've already tested it in the Netscape code base, and it actually runs a little faster and it's a little smaller, so that's good. It's a big win. So let's do this, right? And the committee said, no, we're going to keep it the way it is. But we'll offer you triple equal as a compromise. So, and a lot of people don't like triple equal because instead of having to go, you now have to go, It's like, yeah, triple equal. Always use triple equal.
Does JSLint handle that?
Yeah, JSLint will tell you for sure. Yeah, JSLint will recommend use triple equal.
Would fix it?
Well, it won't fix it. You have to fix your own code. But JSLint is very happy to tell you about all the terrible things you've done, but it's on you to make it right.
Okay.
As it should be. Now there are some cases, because that double equal accidentally does exactly what you want. Should you use it then? And I recommend no, don't even use it then, because you don't want the person who's reading your code to have to ask, did he find the one case where double equal actually does exactly what you want, or is he just incompetent? You don't want people asking that question when they're reading your code, right? You want them to understand what it's doing and go, yeah, this is well-written stuff. I can make this better. So if there's a feature of the language that is sometimes problematic, and if it can be replaced by another feature that is more reliable, then always use the more reliable feature. This is a surprisingly controversial statement, but I think it's obviously true, right? So this is a feature that was added in ES5, multi-line string literals. There are lots of other languages that do this in exactly the same way. I think it was a mistake. First, because it breaks indentation, because the continuation has to be over on the margin. And indentation is really important for understanding the composition of our programs, right? Because we've got nested functions, nested objects, nested blocks. That nesting is critically important, and this breaks indentation, and it does impair readability. That's a bad thing. But worse than that, there is this syntax hazard where this statement is correct, this one is a syntax error. Can anybody spot the error in the second statement?
Is there a space at the beginning of the second line?
Nope.
Space it after the the backslash.
Yeah, exactly. There's a space right here.
Can't you guys see it?
Yeah, it's obvious once it's pointed out, right? But I'm trying to make programs that are perfect. I want to be able to look at it and go, yes, that is perfect. And I can't. So I don't want to use this. We spend a lot of our time searching for the needle in the haystack. We can cut that time down if our programs look less like haystacks. So avoid forms that are difficult to distinguish from common errors. This is another one due to Thompson. He allowed you to put any allowed you to put assignment expressions in condition position of an if statement. Java got this right. Java says you have to put something that evaluates to a Boolean. But then JavaScript got it wrong and went back to the C way and said you can put any expression in there. So this statement appears to do what this one does, but it actually does what this one does. And so you don't ever want to write this one. You want to figure out which one you mean and write that instead. Make your programs look like what they do, and don't make your reader guess, did you get it right or not? Scope is one of the most important inventions in programming. We got it from Algol 60. Almost all modern languages have block scope. JavaScript doesn't. JavaScript only has function scope, which turns out is not a bad thing. That function scope is sufficient for writing good programs. The problem is that most programmers who are writing in JavaScript were trained in Java or C or other C-ish languages and expected to have block scope. And the rules about where you declare variables are different in block scope languages versus function scope languages, and that confusion can cause errors. And this is because of the crazy way that the var statement works. We'll look more at var this afternoon. So because of this craziness, I recommend declare all of your variables at the top of the function, because that is where JavaScript actually will declare them. And so if you put your declarations there, that increases the likelihood that who is ever reading your program will correctly understand what the program is doing. I find the place that gets people the most confused is in the induction variable of the for statement. They really want to say var I there. And I recommend, no, don't even do it there. Move the var I to the top of the function. And they get really upset. And they start screaming. And they say, but that's not how you write it in Java. And I say, write in the language you're writing in. That Java is a different language. They look similar, but it's a different language with a different set of bad parts. In JavaScript, you don't want to be doing that because it doesn't do what you imagine it does. In ES6, which was published in June of this year by the Academic General Assembly, there's now a let statement in JavaScript, which is now starting to find its way into implementations. And when that becomes totally ubiquitous, I will recommend stop using var, use let from now on, because let will respect block scope. Unless your code has to run on IE6, because let is a syntax error on IE6 and your code won't ever run. Or on IE7, or on IE8, or on IE9, or IE10, or IE11. But if you only have to run on Edge 2 or whatever the next one is going to be called, yeah, let. Otherwise, keep using var.
Does the current Edge allow let?
I don't know.
Okay.
It might. I don't know.
Well, I'll be good in 2016 because Microsoft's dropping support for all those IE browsers.
So
Yeah, none of your
Microsoft,
customers will be using those browsers.
yeah, that's the problem. So Microsoft said we're not supporting you guys anymore, but that doesn't mean that the world's going to stop using it. So we're going to be stuck with IE for a while longer, I'm afraid. So global variables are evil in all languages. They cause coupling of things and accidental collisions and security hazards and all sorts of badness. And unfortunately, in the browser, the use of global variables is required because there's no kind of linkage mechanism that allows one compilation unit to find another. They just all share a common global space, which is crazy. So because of that, I recommend in browser applications, use as few global variables as possible, and when you do, name them all in uppercase, because you want them to really stand out as something that is dangerous and important. JavaScript has a new prefix that was modeled after the C++ and Java new prefix. I don't recommend using it ever, but because one of the hazards with it is that if you forget to put the new prefix on the front of a constructor function, instead of creating a new object, it will clobber global variables that happen to have the same names as the instance variables you're trying to initialize, which is awful. And there's no runtime warning, no compile time warning. It's just awful. So because of that, we have a convention in JavaScript that constructor functions should be named with initial caps, and nothing else should ever be named with initial caps. This is the only clue we have as to what requires a new prefix and what doesn't. This is something which is allowed in JavaScript, but it doesn't mean what people expect. So this appears to do what this does. It's going to create two variables, A and B, and initialize them both to 0. What it does instead is it initializes B to 0 and creates A, which will also become a 0. But this one will not be a locally scoped variable. This one will be a global variable. One of the big design errors in JavaScript is if you do not explicitly declare a variable in a function, JavaScript assumes that you intended for it to be a global variable, which was something that was done intentionally to make it easier for the beginners, because often they didn't know what variables were at all. But it makes it much harder for you, because if you're not really careful, any of your variables could turn into global variables where they could easily get stepped on. So again, recommend which one of these you mean and write that instead. Write in a way
Is
that...
it the same way you can declare multiple variables on an var A, comma B, comma C?
Yeah.
Does it B and C or become global variables if you do that?
No, in this comma form, they're okay. The problem is if you use assignment to do that.
Yeah, okay.
So write in a way that clearly communicates your intent. This is another one of Thompson's. So the B language was modeled after BCPL, which was a brilliant little language. BCPL was the first curly brace language. And BCPL got its if statement right, that the parens around the condition were optional, and the curly braces around the consequence were required. Thompson reversed that. Thompson made the parens around the condition required and the curly braces around the consequence optional, because that looked more like Fortran, which was more in the style of the day. So as a result, this statement appears to do what this one does, but actually does what this one does, that it's going to call C unconditionally. And that's someone reading this statement could easily think that C is only going to be called conditionally. That's a bug, right? And so because of this, I recommend always put the curly braces in every time. On every if, on every else, on every while, on every for, every time, put the curly braces in. It's just 2 characters. And it's done. And what that does is, for very low cost, it makes your program much more resilient. It means that someone else is going to come in and add to your if statement. They're going to have a much greater likelihood of being able to do that without introducing an error into it, which is a really good thing. And if you are leaving the curly braces out, you are setting your coworkers up for failure, which is inexcusable and unprofessional. So always put them in. And I hear from people all the time, but you have to go so hard. It's just 2 characters. It's just 2 lousy characters, and they make your program so much better. That as our processes become more agile, our coding must be more resilient, because our programs are never finished, right? There's always going to be constant states of improvement, and we need to code that way. Code our programs so that they are more easily improved over time. So this is the last thing I'm going to complain about Thompson. And again, I have to appreciate Thompson. Thompson gave us Unix. Thompson gave us B, which led to all of our modern languages. Thompson gave us regular expressions. Thompson gave us UTF-8, which I think is one of the smartest things I've ever seen. Thompson has given us some amazing gifts, and as professional programmers, we all owe a tremendous amount to Thompson. Unfortunately, Thompson had terrible taste in programming languages, in programming language design, and even worse than that, he was extremely influential. So all of us have been reading Thompson's designs from our first hours of programming, And we've been doing it so long, it all looks right to us. We cannot see how bad this stuff is and how much it compromises us. So for example, the plus plus operator. This was added to be for doing pointer arithmetic. And we have since determined that pointer arithmetic is harmful, so we don't do it anymore. Modern languages do not support pointer arithmetic. The last popular language to have pointer arithmetic was C++, a language so bad it was named after this operator. But the operator refused to die. It's still in all of our languages, even though we don't need it to increment pointers anymore. So now we use it to add 1 to variables, which is completely unnecessary, but we do it. And unfortunately, it leads to a style of programming in which you try to write one-liners, in which you try to take a whole bunch of stuff and try to smush it down into one line. And that leads to really bad code, stuff which is very hard to maintain, very hard to correct. We've seen security errors, buffer overruns, those sorts of things. This operator is always implicated in those sorts of security errors. And I found in my own practice, anytime I use plus plus anywhere, this thing takes hold of me and I can't control it. It makes me want to take code and try and mush it down in one line. Even though I know that's a stupid thing to do, I can't control myself. This thing takes hold of me, and I start writing really stupid stuff thinking I'm being really smart. So eventually I had to stop because I couldn't do it a little bit. I had to stop completely. So I said, no more plus plus. From now on, it's plus equal 1. And I can relax. And it's easy. I can just write good programs now. Food tastes better. It's just, everything's great. And for a while I thought it was just me, but now I'm recommending everybody plus equal 1 all the time, every time, plus equal 1. It's great, so much better. But I hear from people all the time saying, but I want to be able to write x plus plus because it means the same thing, and instead of having to go, and I can't go, I don't have that kind of time. Except that the typing time is irrelevant. It is completely irrelevant. We don't spend our time typing. But more than that, it's plus plus x, which means about the same thing as x plus equal 1. So anytime I see someone writing x plus plus in increment position, I have to ask, does this clown understand the difference between pre-increment and post-increment? And it means I have to look at every plus plus in his program and ask, did he get this one right? Did he get this one right? Because it's a little dyslexic thing, which it's really hard to tell when you got them reversed. And it causes an off by 1 error that's only off for an instant, but that's enough to cause a bug. And it's really hard to debug those things. The argument in favor of plus plus is that it improves readability, which is bullshit. It does not improve readability. It improves ambiguity. It improves confusion, which are things which are not desirable. So I was reviewing some code and I saw plus plus x plus plus x. So what's going on there? So it's possible that it was a copy and paste error, except the code seemed to be working. So more likely what had happened was someone had done a plus plus x and then someone else noticed, oh, there's an off by 1 problem here. So they did it again. If the original code had said plus equal 1, then the obvious solution would be plus equal 2, right? And it raises a question, why do we think we need completely different syntax for adding 1 to a variable than every other value? How does that make any sense? The answer is, it does not make any sense. But there's this emotional attachment we have to bad grammar in our languages that makes us feel, plus plus that's who I am. It's part of who I am. Like, if you take plus plus away from me, what am I? What's left? So, for no cost, by adopting a more rigorous style, many classes of errors can be automatically avoided. So it occurred to me, so who is writing with bad style? So I came up with 4 classes of bad stylists. And I have to confess, at various times in my career, I have been all of these people. So first are the undereducated. We see this a lot in web developers. We have people who are writing JavaScript now who received no formal training in JavaScript, who taught themselves how to do it by doing view source of some of the worst code ever written, copies of crap going all the way back to Dreamweaver, just awful stuff. And nobody ever told these people, you can do this stuff well, right? They've never seen good examples. It's just sad. Then there's old school. You know, people who are extremely skilled and experienced in one particular language, and now circumstances force them to work in another one where they don't have that same knowledge or experience. We see this a lot now in JavaScript, that Java and C++ guys are having to go into JavaScript because that's where the jobs are, and they're really bitter about it. And they say, okay, I'll write in your JavaScript, but there's no way I'm going to know what I'm doing. That's principle. For some reason, people feel really good about not knowing what they're doing with JavaScript. But in fact, we know that programming is complicated business, and you never want to undertake it in ignorance, but for some reason we feel really good about being ignorant about JavaScript. Then there are the thrill seekers. These are guys who found out, hey, did you know you can put your semicolon at the beginning of a statement instead of at the end, and sometimes it works? Ah! And so they just write this stupid-looking crap just because. I think people like that should have to wear helmets when they're coding. And finally, the exhibitionists. These are people who will study the standards, study the implementations, find all the weird corner cases, and there are a lot of weird, bizarre corner cases in this language, and intentionally use them in everything that they write. Stuff where you look at it and go, what the hell is that supposed to mean? And they're proud of it. They go, look at that, you have no idea what that means, you know, but they're doing that. And they'll say, that was intentional. I know what I'm doing. And I say, no, if you knew what you were doing, you would not be doing that. So I need to say something about performance, because I sometimes hear the need for performance as the excuse for why we can't have good style. And it turns out those arguments are all wrong. Performance-specific code is usually crufty because we're removing generality from the code. We're increasing code or paths through the code, which makes testing and maintenance all much harder to do. Clean code is much easier to reason about, so we should try to keep our code as clean as we can for as long as we can. Donald Knuth of Stanford said that premature optimization is the root of all evil, which is true. We should not attempt to optimize any code until we have measured it. We should then do the optimization. We should then measure again. And if we did not get a significant improvement, then we should consider the change to be a bug and back it out. If the reason we added cruft to the code base was to make it faster, if we didn't actually obtain a significant performance increase, then it fails, and we should remove that code. So measure twice, cut once. Turns out most code has a negligible impact on performance, so we should only bother with optimizing the code that is taking the most time. You have only a limited amount of time for doing optimization, so you don't want to waste that time optimizing code that doesn't matter. You need to optimize your optimizing. And finally, algorithm replacement is vastly more effective than code fiddling. So if your code is slow because you've got an n-squared loop, fiddling with the details of the inner loop will have no effect on significantly increasing n. The only thing that could work is replacing that code with a different algorithm, you know, maybe an n log n algorithm, which can then get you a much larger n. And that kind of change is much easier to do if the code has not already been pre-optimized. Programming is the most complicated thing that humans do. Computer programs must be perfect, and humans are not good at perfect, especially me. I am a deeply flawed human being. But I'm a pretty good programmer, but it requires a tremendous amount of effort and discipline. So designing a programming style demands discipline. It is not selecting features because they are liked or pretty or familiar. It's because it helps you to reduce your error rate. The alternative is spending more time in the abyss. You know what I'm talking about. That's that cold, dark, hurtful place we descend into where we go and battle the demons and kill the bugs. When I first started programming, it was wonderful. I was having this epiphany. I thought I had this new way of understanding everything in the world, and I thought it was great, and I thought everybody should learn how to do this, because this is really exciting stuff. I don't believe that anymore. I think that we are able to do programming because there's something seriously wrong with us. Normal people can't do this. If a normal person goes down into the abyss, they come right back up and say, I'm changing majors. I don't know what's wrong with you people. I'm out of here. We're able to do this because of this amnesia thing that we suffer from, that we forget how much time we spend down there and how awful it is when we're down there. And that's what allows us to go down there again. Also, we're tremendous optimists, that we think that we can actually go down there and win and come back. And that's a great thing. You know, I don't think you can be an optimist and be a programmer, or you got to be an optimist to be a programmer. It's just necessary. That's also why we can't schedule worth crap, right? How long is that going to take? And go, oh, well, it's about that many keystrokes, so it should take about that long. We forget about that, right? That's where most of the time goes. So if you want to be more effective, more productive, figuring out a way to stay out of there, that's the big win. Figuring out how to reduce your keystrokes is irrelevant, right? You want to optimize the thing that's taking your time, and the thing that's taking your time isn't the typing, it's that. So the JSLint style was driven by the need to automatically detect defects, and that forms that can hide defects are considered defective, even if they are not bugs at that instant. So when I was developing JSLint, there was a thing called comp.lang.javascript on the Usenet. And there was an endless stream of people saying, my program doesn't work, can someone tell me why? And so I would take them and I'd throw them in JSLint, and sometimes I'd go, there it is. And sometimes I'd go, couldn't, why is that? And sometimes it was because they were using forms which made further analysis of the program impossible. And eventually, reluctantly, I came to decide that, well, if you're writing that way and you don't need to, then that's a problem. Because we want to make our programs make the errors stand out. And you can do that by writing better all the time. So the idea of subsetting the language is not an original idea. That for virtually every language, you want to subset it. It's been said only a madman would use all of C++. It's also been said only a madman would use C++, but that's for another time. And there's something nice about having everybody using the same subset. Every team writing C++ will figure out how much of the language they want to use. And that's fine until they now have to take over someone else's code and go, oh, friends, crap, and you have to deal with that stuff. So if we could get everybody using the same subset, that makes interoperability a lot easier. So there will be bugs. I'm not promising that you're going to be bug-free if you adopt a better programming style, but you can move the odds to your favor, and you definitely win, and you do that at no cost.